Hi everyone! In this video we'll do more examples of antiderivatives involving the linear over irreducible quadratic partial fractions. In the previous video I suggested integrals of this form really only require two ingredients. The first ingredient was f prime over f, and the second was sums and differences of squares. You can pause and check that the question given here cannot be put into the f prime over f form, so immediately we know we need to have a sum of squares. In this case, that requires us to complete the square, so let's try it. Start by grouping the first two terms inside a set of brackets. Then we add and subtract 4. You can pause and check for yourself that that's the correct value. After that, we can form our sum of squares as shown here, and again, just pause and check if necessary. Now, the real reason we want a sum of squares is so that we can make use of inverse trig formulas. So we want to think of the denominator as something of the form u squared plus a squared. But in order to do that, we need to perform the substitution where u equals x minus 2. In that case, du is exactly the same thing as dx, and so that makes for a pretty nice substitution so far. But we still have to deal with this x plus 3 in the numerator. Anytime we have an x left over after substituting, we should ask whether it can be put into terms of u. To do that, we go back to our substitution and ask what x is equal to. With a bit of basic algebra, we can see that x is the same thing as u plus 2 in this case, and so wherever we see an x, we can literally replace it with u plus 2. And with that, we've got everything in terms of u, which is good, although we may as well clean up our numerator before going any further. After going through so many details, don't forget what we were trying to do in the first place. We were trying to form a sum of squares so that we could make use of inverse trig formulas. And at this point, we can see the arctan formula could be used if the numerator were just a constant. So that motivates us to break up our fraction at this stage. Our first term would have a numerator of u, and our second term would have a numerator of 5. Notice I also pulled the constant 5 out front just for convenience. Our second term here now looks exactly like our arctan formula, where in this case a is the square root of 5. So we can state the antiderivative of that term and turn our attention to the first term. What you'll notice with the first term is that it's of the form f prime over f, if we were to multiply the numerator by 2. And we can do that as long as we also divide by 2 to correct that change. Then this f prime over f integral works out the same way as always. Just take the natural log of the denominator with an absolute value. Actually, the absolute value is technically not needed in this case because u squared plus 5 represents a value which is already positive. So if you like, you can actually drop the absolute value here and also just make sure to express your final answer in terms of x and you're finished. The example we just did suggested that these linear over irreducible quadratic integrals can be quite a lot of work. So let's take a moment to organize what your thought process should look like, at least for this case where k equals 1 that we've been talking about. The first thing you should always do is check whether you can force an f prime over f structure. If you can do that, then you're basically done, because we know the result is always just the natural log of the denominator with an absolute value in that case. If you cannot form an f prime over f structure, that's when things get a little more complicated. But it does play out exactly the same way every single time. When f prime over f fails, always look for a sum of squares. In order to find one, keep in mind that you might need to complete the square first, and once you have a sum of squares, then you should be set up to use the arctan formula, perhaps with an appropriate substitution first. However, the example we just did showed that it might also be necessary to break up your fraction before using the arctan formula, but at that point, you're basically done. So although these integrals can seem overwhelming as you get used to them, you can be assured that the same steps will work every single time, so it's just a matter of practicing. And I want to emphasize that the strategy we just discussed is really only applicable for the k=1 case. A similar but slightly different strategy is needed when k is not 1, but unfortunately we don't have all the tools to handle that yet, so we'll come back to that in the future when we're ready for it. Taking everything we just said into consideration, pause here and see how far you can get with this question. When you're ready to look at the answer, let's continue. The very first thing to do, as always, is ask whether this can be viewed as f prime over f. Unfortunately, this one cannot be. So we know right away that we need to find a sum of squares. And for that, we need to complete the square. Start out the same way as always by grouping the first two terms. But notice x squared has a visible coefficient in this case, which does make completing the square a little bit trickier. When that happens, we need to factor the 3 outside of these brackets, and we would then end up with x squared plus 2x inside the brackets. That's because the 3 got factored out from both the terms. So the 6x, when I factored out a 3, became a 2x. Next, as always, we grab the coefficient of x, which in this case is 2. We divide that by 2 and square the result, which gives a value of 1 in this case. So we add the 1 inside the brackets, but now you need to be careful. Because the 1 was added inside the brackets, it also gets affected by this multiplication by 3. And that means what we really added wasn't just 1, it was 3 times 1, or in other words, we added 3, technically speaking. So it's necessary to subtract 3 to negate the change that we just made. If this seemed at all mysterious to you, make sure to review the videos on completing the square, which would explain how this works in more detail. But if you accept what we just did, we know 14 minus 3 can be simplified to plus 11. And the brackets, as always, can now factor nicely. So now going back to the integral that we've been asked for, there's more clearly a sum of squares in the denominator. To emphasize that, though, we might want to write the denominator in a way which is more clearly of the form u squared plus a squared. This just gives us more visibility about what substitution we should be making in the next step. In this case, though, the substitution that we need is a little bit tedious because of the need to carry this square root through all of the next steps. So I'll say that although this approach will get the job done, and you can even check that for yourself if you want, there's actually another way which I think is less tedious. So there's really two options here, but the option I would choose to go with is to factor out this 3 instead of including it as part of our sum of squares. So let's see how this alternative approach would work. We could pull this constant all the way out front of our entire integral. Just be mindful that in doing so, this factoring would affect all the terms in the denominator, so our 11 becomes 11 divided by 3. Now we can still think of this denominator as u squared plus a squared, but now the correct substitution would be u equals x plus 1, making for what I think is a much nicer substitution compared to our first attempt where we didn't factor out the 3. Under this substitution, we know du is the same thing as dx, but we still have this x left over, which we need to express in terms of u. So we go check what x is equal to. In this case, that would be u minus 1. And then changing our x into u minus 1 completes the substitution, so we're almost at the finish line. Here I've just summarized what we know so far, and we may as well do some cleanup in our numerator here by collecting like terms as well. So pause and check that expanding and simplifying gives us 2u plus 3 on the top. And after working through so many details, don't forget what path you were on in the first place. So everything we've done so far had the sole purpose of giving us a sum of squares. Why? So that we can make use of inverse trig formulas. In particular, arctan seems to be the relevant one in this case. So that's why we completed the square, that's why we did a substitution. It was all to get the sum of squares in the denominator. So let's start thinking about how we can use arctan at this stage. The arctan formula requires that we only have a constant in our numerator, but if you take just this section that I'm circling now, you can see that part really does resemble that arctan formula. So for that reason, we're motivated now to break up our fraction. Our first term, if we do that, would have a numerator of 2u, and don't forget the 1/3 in front. Our second term has a numerator of 3, and again, don't forget the 1/3 in front, which needs to apply to both terms after we split our fraction. As a matter of cleanup, we may as well cancel these 3's as well, leaving us with just a 1 in the numerator. And sure enough, this now exactly matches our arctan formula, where a has a value of root 11 over 3 in this case. All that remains now is to deal with the first term. But that one is of the form f prime over f. That's actually always the way it's going to work out. If it's necessary to break up the fraction at this stage, the remaining term will always be of the form f prime over f every single time. And so our final answer will always contain one term with a natural logarithm and another term with an arctan. In that sense, there's predictability in terms of where what the answers to these types of problems should look like, even if the steps we took to get that answer can be a little long and tedious. Also, don't forget to express your final answer in terms of x. At this stage, all that's left is to practice on your own, so I'll end the video here and I'll see you next time.